The universe began with an explosion, not a mere detonation of matter, but the sudden expansion of space itself. From that moment of incomprehensible violence, every galaxy, star and planet has existed in a cosmic landscape shaped by destruction as much as by creation. In the tranquil beauty of the night sky, we see the illusion of stillness. Stars twinkle gently, galaxies spiral in serene elegance. But beneath that calm exterior lies a universe of unimaginable fury. Stars collapse in seconds, releasing more energy than billions of suns combined. Magnetars tear themselves apart with magnetic fields strong enough to distort atomic structure. Entire galaxies are momentarily illuminated by the death cry of a single star. These are cosmic catastrophes, the universe's most violent events. They are not random outbursts, but the very engines of cosmic evolution. They forge the elements that build planets and people. They send shockwaves of radiation that can sterilize entire worlds. And they are, paradoxically, the reason we exist at all. Over the next hour, we'll dive deep into the nature of these apocalyptic explosions, from the collapse of massive stars to the bursts of gamma rays that sweep across billions of light years. We'll follow the story of how scientists first detected these events, the mysteries that still haunt astrophysics, and what these violent outbursts reveal about the fundamental laws of reality. Our journey begins at the source, with the stars themselves. Every star is a battlefield, a delicate balance between two opposing forces. In its core, gravity relentlessly tries to crush everything inward. Pushing back is the star's nuclear furnace, where hydrogen atoms fuse into helium, releasing an immense amount of energy. This outward pressure, this radiation, is what keeps a star like our Sun stable for billions of years. But this stability is temporary. A star's life is defined by its fuel, and when that fuel starts to run out, the balance tips for stars many times more massive than our Sun. The end is not a quiet fade into darkness. It is a cataclysmic finale of epic proportions, a supernova. As a massive star exhausts its primary fuel, gravity gains the upper hand. The core begins to collapse under its own immense weight. Temperatures and pressures skyrocket to unimaginable levels, triggering a final, frantic burst of fusion. Heavier and heavier elements are forged in a matter of seconds: carbon, oxygen, and finally, iron. But iron is a dead end. Fusing iron doesn't release energy, it consumes it. With its energy source gone, the star's core collapses catastrophically. In less than a second, a region the size of Earth is crushed down to a ball just a few dozen kilometers across. This isn't just a collapse. It's a cosmic ricochet. The infalling outer layers of the star slam into this newly formed, incredibly dense core and rebound with ferocious power. This outward-bound shockwave is the supernova explosion. The spectacle is breathtaking. For a few weeks, a single dying star can outshine its entire galaxy, blazing with the light of hundreds of billions of suns. The energy released is so vast it's difficult to comprehend. But it's not just light. The explosion flings the elements forged during the star's life and in its final explosive moments far out into space. This stellar debris, enriched with carbon, oxygen, and iron, becomes the raw material for the next generation of cosmic creation. The iron in your blood, the calcium in your bones, the oxygen you breathe all were forged in the heart of a dying star and scattered across the galaxy by these violent explosions. We are, quite literally, made of stardust. But what happens to the core that's left behind? Depending on its mass, it can become one of two of the most extreme objects in the universe. If the core is massive enough, gravity wins completely, crushing it beyond all known limits of physics into a singularity black hole. Its gravitational pull is so strong that not even light can escape its grasp. But if the core is slightly less massive, it becomes something else. An object where the very nature of matter is pushed to its absolute limit. A neutron star. Imagine taking a star 1.5 times the mass of our Sun and crushing it into a sphere no bigger than a city. The density is staggering. A single teaspoon of neutron star material would weigh billions of tons. These neutron stars are born spinning incredibly fast, a consequence of conserving the angular momentum of the original, much larger star. Some spin hundreds of times per second. As they spin, their powerful magnetic fields sweep through space like cosmic lighthouses, emitting beams of radiation. If one of these beams happens to sweep across Earth, our radio telescopes detect a regular pulse, and we call the object a pulsar. For years, this was the end of the story. A supernova happens, leaving behind a beautiful nebula and a dense spinning remnant. But then, astronomers started detecting something far more powerful, a mystery that would point to an even more violent cosmic event. They were detecting bursts of high-energy radiation, gamma rays, that were not coming from within our galaxy, but from the farthest reaches of the observable universe. These were the gamma ray bursts.
Look up at the night sky. What do you see? A quiet, peaceful expanse of twinkling lights. But that tranquility is an illusion. Out there in the silent dark, the universe is a stage for the most violent and spectacular explosions imaginable. Events so powerful they can outshine entire galaxies and forge the very elements that make up our world, our bodies, and our blood. Today, we're journeying into the heart of these cosmic cataclysms, to uncover the story of how stars die, and in doing so, how they give birth to everything we know. Every cosmic explosion begins with a single, ancient process, the life cycle of a star. Imagine vast cold clouds of gas and dust drifting through interstellar space. Over millions of years, gravity, the universe's master sculptor, begins to pull this material together. It clumps, it compresses, and the pressure at its core skyrockets until something magical happens. Nuclear fusion ignites. A star is born. This marks the start of a star's main sequence, a long, stable period defined by a delicate balancing act. The immense inward crush of gravity is perfectly counteracted by the furious outward push of nuclear fire burning in its core. For stars like our Sun, this cosmic ballet will last for about 10 billion years along. Peaceful life. But not all stars are so serene. The true giants of the cosmos, stars tens or even hundreds of times more massive than our Sun, live fast and die young. They burn through their nuclear fuel at an astonishing rate. Their lives aren't measured in billions of years, but in mere millions. And when their fuel gauge hits empty, the delicate balance shatters, and stability gives way to absolute chaos. This is where the story of cosmic violence truly begins. Inside the core of one of these massive stars, a frantic alchemy is underway. Fusion is like a cosmic forge, smashing lighter elements together to create heavier ones. Hydrogen fuses into helium, helium fuses into carbon, carbon into oxygen, and so on, climbing the periodic table through neon and silicon. But this process has a final, fatal endpoint: iron. Iron is the ash of stellar fusion. Unlike the elements before it, fusing iron atoms doesn't release energy. It consumes it. When a critical amount of iron builds up in the star's core, the nuclear furnace sputters and dies. The outward pressure that held the star up for millions of years vanishes in an instant. The delicate equilibrium crumbles. What happens next is almost too fast to comprehend. With nothing to stop it, gravity wins the long war. In less than a single second, the star's core collapses on itself, reaching speeds of a quarter the speed of light. The temperatures soar to hundreds of billions of degrees hotter than anything else in the universe. In this inferno, electrons and protons are crushed together to form neutrons, releasing an unimaginable blast of ghostly particles called neutrinos. These neutrinos carry away most of the collapsing star's energy, fleeing the scene of the crime. The star's outer layers, suddenly left with no support, plunge inward. They slam into the newly formed, incredibly dense neutron core and rebound with cataclysmic force. This is a supernova, one of the most spectacular events in nature. For a few days or weeks, the dying star can shine brighter than its entire home galaxy of 100 billion stars. The explosion sends powerful shock waves ripping through space, scattering all those heavy elements forged in its core: the iron, the gold, the uranium across the cosmos. Supernovae are the universe's ultimate recycling engines. Without them, the cosmos would be a boring place, made of only hydrogen and helium. Every atom of calcium in your bones, every atom of oxygen you are breathing right now, was forged in the fiery death of a distant, long-gone star. We are quite literally made of stardust. But even among these colossal explosions, some go far, far beyond what we thought was possible. Some stars don't just die, they unleash something even more extreme. A typical supernova is mind-bogglingly powerful, releasing as much energy in a few seconds as our sun will over its entire 10 billion year lifetime. But what happens when the star is exceptionally massive, say, over 30 times the mass of our sun? In these titanic deaths, the collapsing core doesn't stop at becoming a neutron star. Gravity's victory is absolute. The core continues to collapse, crushing matter into an object so dense that its gravity warps space-time itself, an object from which not even light can escape: a black hole. As the star's outer layers rain down onto this newborn black hole, they form a swirling, superheated disk of matter, like water spiraling down a drain. In some very special cases, immense and powerful magnetic fields grab some of this infalling material and channel it into two narrow, focused jets. These jets blast outward from the star's poles at nearly the speed of light. And if, by sheer cosmic chance, one of these jets happens to be pointed directly at Earth, we witness the single most energetic explosion in the known universe, a gamma-ray burst, or GRB. For just a few brief seconds, a single GRB can outshine every other star in the observable universe combined. It is the flashbulb of creation, marking the violent birth of a black hole. These events are incredibly rare in any one galaxy, but the universe is so vast that our space observatories detect several of them every week. Each one is a message from the edge of physics, a momentary glimpse into the most extreme processes in the cosmos. And yet, they remain shrouded in mystery. What exact mechanism powers their immense energy? How do they create such incredibly tight, focused beams of radiation? But perhaps the most profound question is not how they happen, but why they matter. These cosmic explosions aren't just random acts of destruction. They are fundamental agents of creation. Each cataclysm seeds the interstellar medium with the heavy elements necessary for planets and for life. The shock waves they create can trigger the collapse of new gas clouds, kickstarting the next generation of star formation. In that sense, Every act of cosmic violence helps set the stage for life to emerge. If the universe were a perfectly calm, unchanging place, if no stars ever died in fire and fury, there would be no Earth, no oceans, no us. We exist because stars explode. The story of cosmic catastrophes isn't a story of chaos, but of a grand cosmic balance. It's the ongoing cycle of creation and destruction that defines the universe itself. Some stars die quietly, fading into cold, dark embers. But others scream across the cosmos in a final, brilliant burst of furia, last testament from the very edge of physics itself. In the deep theater of the universe, certain cosmic events stand apart, not merely as explosions, but as singular performances of physics pushed to its absolute limits. These are the most violent acts ever recorded by human instruments: gamma ray bursts, magnetar flares, and hypernovae. Each one is a window into a different extreme of nature. Together, they form a kind of trinity of cosmic catastrophes, three ways the universe reveals what happens when energy, gravity, and quantum mechanics collide in the most spectacular fashion. Let's begin with the most terrifying and mysterious of all, the gamma ray burst. Back in 1967, at the height of the Cold War, the United States launched a series of satellites known as the Vela Project. Their mission was simple: to detect secret nuclear explosions on Earth, which would have violated the 1963 Nuclear Test Ban Treaty. But soon, these satellites began recording something completely unexpected: brief, intense bursts of gamma radiation coming not from Earth, but from deep space. Each flash lasted only a few seconds, yet in that tiny window, it released more energy than our sun will emit in its entire 10 billion year lifetime. At first, scientists were stumped. Could these be signs of alien weapons, or maybe some new type of supernova exploding nearby? For decades, the true origin of these bursts remained one of astronomy's greatest mysteries. Then, in 1997, the Italian-Dutch satellite Bepo-ACX finally cracked the case. It managed to pinpoint the fading afterglow of a gamma ray burst, known as GRB 970,508, and traced it to a galaxy billions of light-years away. That single discovery changed astrophysics forever. It meant these explosions were cosmological and imaginably distant, yet so powerful they were still visible across the known universe. Their power was simply beyond comprehension. So what exactly are these cosmic flashbulbs? Turns out there are two main types: long-duration gamma ray bursts, which last more than 2 seconds, are tied to the collapse of the most massive stars in the universe, specifically in events called hypernovae that give birth to black holes. Then there are the short-duration bursts, lasting less than 2 seconds. These are even more exotic, produced when two superdense neutron stars smash into each other, an event so extreme that it momentarily warps space-time itself. In both scenarios, the basic principle is the same: a sudden, catastrophic release of energy from incredibly compact matter. When a massive star collapses, for instance, the material falling inward forms a swirling disk around the brand-new black hole at its center. Intense magnetic fields get twisted up and focus some of this superheated plasma into two narrow, relativistic jet beams of matter moving at over 99.999% the speed of light. These jets then punch through the dying star's outer layers and erupt into space, unleashing a torrent of high-energy photons that we see as gamma rays. If Earth happens to be in the direct path of one of these narrow beams, our detectors see it as a brief but blinding flash of gamma ray burst. Fortunately for us, these events are mercifully rare. Astronomers estimate a GRB occurs somewhere in the observable universe every few minutes. But only 1 in a billion will ever point directly toward Earth. Still, the implications are sobering. A nearby GRB, even 1,000s of light-years away, could strip Earth's atmosphere of its protective ozone layer, exposing the surface to lethal ultraviolet radiation from our own sun. Some researchers have even speculated that such an event might have contributed to a mass extinction here on Earth hundreds of millions of years ago. In the cosmic lottery of catastrophe, it seems humanity has just been incredibly lucky. If a gamma burst is the blinding signal, the hypernova is the colossal engine driving it. The term hypernova describes a supernova so energetic that it defies ordinary classification. A typical supernova releases around 10 to the power of 39 joules of energy. A hypernova can unleash 10 times more. In 1998, astronomers witnessed a stunning example, supernova 1998 BW, at almost the exact same time. Satellites recorded a long-duration gamma-ray burst, GRB 980,425, coming from the same spot in the sky. The connection was undeniable. For the first time, humanity had witnessed a supernova powerful enough to generate a GRB. This discovery suggested that hypernovae aren't just bigger than average stellar deaths. They are the violent birth cries of black holes. As the star's core collapses, part of its mass falls inward, creating the black hole. The rest of the star is blasted outward in an explosion of unimaginable violence, seeding the cosmos with newly forged elements. In that single brilliant instant, a new black hole is born and, so paradoxically, is the new matter that will one day form planets, stars, and maybe even life. But not all cosmic explosions come from the birth of black holes. Some arise from a different kind of monster, one born from the wreckage of a supernova, the magnetar. Magnetar is a special type of neutron star, the incredibly dense core left behind after a massive star explodes. To get an idea of just how dense, imagine compressing our entire sun into a sphere just 20 kilometers wide, smaller than most cities. Give it a magnetic field, 1 trillion times stronger than Earth's. That's a magnetar. Its surface is a crust of atomic nuclei, crushed so tightly together that a single teaspoon of magnetar material would weigh a billion tons on Earth. Inside, matter exists in exotic states we can barely imagine, perhaps as a superfluid of neutrons, or something stranger still. Occasionally, a magnetar's immense magnetic field becomes unstable and violently rearranges itself. This starquake releases a colossal burst of gamma rays and X-rays, known as a magnetar flare, which can briefly outshine an entire galaxy. In December 2004, one such event, from a magnetar named SGR 1806-20, shook the cosmos. Located about 50,000 light-years from Earth, it erupted with an energy equivalent to trillions upon trillions of nuclear bombs. For a brief moment, it completely overwhelmed satellites and detectors all across our solar system. Had it been just 10 times closer, it could have seriously disrupted Earth's upper atmosphere. These magnetar flares are more than just astronomical curiosities. They are natural laboratories for studying the strongest magnetic fields known in the universe. They allow physicists to test the very limits of quantum electrodynamics, how light and matter behave when the fabric of space itself becomes magnetized, though often overshadowed by their rarer, more extreme cousins. Ordinary supernovae are far from ordinary. Every few seconds, somewhere in the universe, a star explodes in one of two main ways. We've already talked about core collapse supernova from the deaths of massive stars. The other kind are type Ia supernova. These happen in binary star systems, when a small, dense star called a white dwarf pulls too much material from its companion star, becomes unstable, and completely detonates. These explosions serve as vital cosmic beacons, because type Ia supernova always explode with roughly the same brightness. They act as standard candles, allowing astronomers to measure vast distances across billions of light-years. In fact, it was by studying these very explosions in 1998 that scientists made a profound discovery. The expansion of the universe is accelerating, driven by a mysterious force we now call dark energy. Even in their death, stars teach us about the ultimate fate of the cosmos. Each of these events, gamma-ray bursts, hypernovae, magnetar flares, and supernova, represents a different face of the same fundamental truth. The universe is not a gentle, quiet place. It is dynamic, unstable, and profoundly creative. Through violence, it builds complexity. Through collapse, it creates light. And through destruction, it makes new life possible. For every explosion we manage to detect, countless others go unseen, hidden behind veils of cosmic dust, happening in galaxies too far away for our instruments to reach. But as our technology advances, humanity's window into this violent universe is widening. We've seen the explosions. We've measured their fury. But the deeper we look into these cosmic catastrophes, the more they challenge the very laws of nature as we know them. What truly powers a gamma-ray burst at its core? What happens inside a collapsing star when physics itself begins to break down? Could these colossal forces be telling us something deeper about the nature of space-time itself? The next chapter begins where certainty ends, in the mysteries still hidden inside the brightest lights of the universe. Every explosion we've ever seen, from the tiniest firecracker to the most massive supernova, can be described, modeled, and measured. We understand the physics. But when we look out into the cosmos, we find events so violent, they don't just test our theories, they threaten to shatter them. Matter collapses faster than light can escape, and energy densities surge beyond anything our equations can handle. This is where we reach the absolute limit of human understanding. So today, we're going beyond the spectacle of cosmic fireworks and asking, what are the 5 deepest mysteries hidden inside the universe, ES's most violent explosions? Let's start with one of the biggest puzzles in astrophysics. What truly powers gamma-ray bursts? We know the basic story. A massive star dies, collapses into a black hole, and launches jets of energy that tear across space as gamma rays. But how asterisk? How is that incredible energy extracted, and why is it focused into such tight beams? The leading theory is the collapsor model. Imagine a massive spinning star collapsing. As its material spirals into the newly formed black hole, powerful magnetic fields in the surrounding disk are thought to grab, twist and funnel twin jets of energy out through the star's poles. It's a compelling idea, but it has problems. Focusing these jets requires very specific magnetic conditions that might not always exist, and the sheer efficiency is baffling. How can less than one sun's worth of material unleash the energy of hundreds of thousands of supernova? It pushes the limits of what we think is possible. It brings us to a rival idea, the magnetar model. This theory suggests that some gamma-ray bursts aren't powered by black holes at all, but by magnetars incredibly dense, rapidly spinning neutron stars with magnetic fields a quadrillion times stronger than Earth's. When one of these is born from a stellar collapse, rotating hundreds of times per second, its immense magnetic energy can be unleashed as a powerful, relativistic wind. This could explain certain gamma-ray bursts that have unusually long afterglows, as if a central engine is continuously pumping energy into the explosion long after the initial flash. So, which is it? A black hole or a magnetar? The truth is, both models fit some of the data, but neither fits all of it. The reality might be a mix of both, or something entirely new. Recent observations from NASA's Fermi telescope have added another layer of complexity. Some bursts produce incredibly high-energy photons that arrive seconds, asterisk after asterisk, the main flash. This delay suggests the energy release isn't a single event, but a layered process, with different mechanisms happening at different stages within the jets. Gamma-ray bursts aren't just explosions. They're cosmic laboratories where relativity, magnetohydrodynamics, and quantum physics collide. Now, for our second mystery, the nature of black hole jets. When a black hole forms, whether from a collapsing star or merging neutron stars, it sometimes launches colossal jets of plasma that can stretch for light years. These jets travel at nearly the speed of light, somehow confined and accelerated by magnetic fields. But how? General relativity tells us how matter warps space-time around a black hole. But it doesn't explain how energy can escape from such a region in these narrow, focused streams. The most popular idea is the Blandford-Zniak process. It proposes that as a black hole spins, its rotation can twist the magnetic fields around it, effectively turning the black hole into a giant dynamo that converts gravitational energy into a powerful outward blast of radiation. But confirming this is almost impossible. We couldn't see inside a jet or measure the magnetic field right at the edge of the event horizon. All we can observe are the after effects, radiation patterns, and faint echoes of light. Even the incredible Event Horizon Telescope, which gave us that first iconic image of a black hole's shadow, could only hint at how these jets form. The truth remains hidden behind a wall of complex math and observational limits. If we could crack this puzzle, we might finally understand how gravity and electromagnetism, two of nature's fundamental forces, work together in the most extreme conditions imaginable. This leads us to an even deeper question, our third mystery. What happens in the final moments of a star's collapse? We can simulate the process with computers, but only up to a certain point. It's the moment the density inside the collapsing core exceeds that of an atomic nucleus, our models break down. Inside that crucible, matter enters states that defy our comprehension, perhaps a quark gluon plasma, or even exotic particles we've only theorized. This is where the two pillars of modern physics, general relativity and quantum mechanics, go to war. One describes gravity on a cosmic scale. The other describes particles and forces on the smallest scale. Neither can fully explain what happens in those final, frantic milliseconds. Does the core just keep collapsing into a singularity, a point of infinite density, as relativity predicts? Or do quantum effects step in and create a barrier, a new state of matter, or even a bounce? Some speculative theories, like loop quantum gravity, suggest that singularities might not exist at all. Instead, matter could rebound in a phenomenon known as a Planck star, releasing a burst of radiation as it expands. If this happens, it might produce a unique Gamma signature we could one day detect. So far, we've found no such evidence. The violent death of a star isn't just an astrophysical event, it's a direct probe into the deepest conflict in all of science. Our fourth mystery takes us into one of the most extreme environments in the cosmos, the magnetic fields of magnetars. These fields can exceed 10 quadrillion times that of Earth's. In such an intense environment, the vacuum of space itself begins to behave strangely. Physics predicts that photons can spontaneously split into pairs of particles, and quantum fluctuations become a dominant force. This is the realm of quantum electrodynamics, where QE a scale so extreme we can't replicate it in any lab on Earth. When magnetars flare, it might briefly push the universe into this exotic state, allowing us to witness phenomena like vacuum birefringence, where empty space itself can bend light. Studying these flares is like using the cosmos as the ultimate particle accelerator to test the absolute limits of quantum field theory. But we've barely scratched the surface. We've only recorded a handful of these flares in detail. Each new observation is a precious opportunity. It's a chance to find a crack in our current understanding of physics and maybe, just maybe, rewrite the textbooks. And this brings us to our fifth and perhaps greatest mystery, the connection between cosmic catastrophe and cosmic creation. Why does the universe produce such incredibly destructive phenomena, and what role do they play in its long-term evolution? Every Gamma burst or hypernova, while locally devastating, serves a purpose. They are cosmic engines of redistribution, scattering heavy elements, the building blocks of planets and life across galaxies. But could their influence be even greater? Some scientists propose that the shock waves from these powerful bursts could compress nearby gas clouds, triggering the birth of new stars. Others wonder if they could influence biological evolution on a galactic scale, periodically resetting ecosystems on habitable worlds. On an even grander scale, could these explosions play a role in the universe's overall energy balance, acting as cosmic release valves for gravitational energy as galaxies evolve? These ideas are still speculative, but they point to an important truth. Cosmic catastrophes aren't just random acts of violence. They are a fundamental part of the machinery that keeps the universe dynamic, fertile, and constantly changing. Every time we peer deeper into these explosions with optical telescopes, gravitational wave detectors, or neutrino observatories, we peel back another layer of the cosmic onion. But we are still so far from the core. The coming decades promise a new generation of instruments that will give us an unprecedented view of these events. The Vera Rubin Observatory will map the sky for transient flashes of light. The LISA space antenna will listen for the gravitational rumbles of distant mergers. And future Gamma missions will capture the most energetic photons streaming from the heart of stellar collapse. With each new detection, we move a little closer. We're not just trying to understand how the universe explodes. We're trying to understand what those explosions reveal about its deepest, most fundamental laws. When we look up at the stars, we often think of them as distant, harmless lights, background decoration for our planet's story. But in truth, those stars write the story. They determine not only how life begins, but how it might end. Cosmic catastrophes, supernova, hypernovae, gamma ray bursts may be rare, but their reach can extend across unimaginable distances. In the right conditions, one such explosion could undo millions of years of biological evolution on Earth in a matter of seconds. Let's explore what would happen, not in science fiction, but in physics. Among all cosmic explosions, gamma ray bursts, or GRBs, are the most dangerous to life as we know it. Their intense beams of high-energy photons, gamma rays, and X-rays can travel unimpeded for billions of light years. If one were aimed directly at Earth, the consequences could be catastrophic. But GRB's energy output is tightly focused into a narrow jet, usually just a few degrees wide. Within that cone, the energy density is staggering, enough to strip atmospheres, destroy ozone layers, and alter planetary climates. Astronomers estimate that a GRB within 5,000 to 10,000 light-years of Earth could severely damage our biosphere. The key danger isn't the immediate heat or light, it's atmospheric chemistry. High-energy gamma rays collide with nitrogen and oxygen molecules in our atmosphere, producing nitrogen oxides that rapidly deplete our ozone layer. Without ozone, deadly ultraviolet radiation from the sun would reach the surface unchecked, sterilizing the land and shallow oceans. The damage wouldn't be instant, it would unfold over weeks or months. First, a blinding flash of radiation would ionize the upper atmosphere. Then, the ozone layer would thin dramatically, leading to widespread DNA damage in exposed organisms, total crop failures, and mass extinction cascades. Any recovery would take centuries, if it happened at all. Has this kind of catastrophe ever happened before? There's growing evidence that it might have in our planet's distant past. In 2003, astrophysicists Adrian Mellett and Brian Thomas proposed that a gamma ray burst could explain a mysterious mass extinction event that occurred roughly 450 million years ago at the end of the Ordovician period. This extinction wiped out about 85% of all marine species, particularly those living near the ocean surface, where ultraviolet light penetrates most deeply. The pattern of extinction fits perfectly with what we'd expect if Earth's ozone layer had been stripped away. There's no evidence of an asteroid impact, no massive volcanic activity, no layer of telltale debris, just a silent, invisible cosmic flash from light years away. It's a chilling reminder that the universe doesn't need to aim asteroids at us to erase life. Sometimes all it needs to do is blink. Gamma ray bursts are directional and rare. Supernova, however, are not. They occur much more frequently, about 2 or 3 times per century in a galaxy like ours. Most are too distant to affect us. But a supernova detonating within 30 light-years of Earth would have severe consequences for our biosphere. When a massive star explodes, it unleashes a flood of high-energy radiation, including cosmic rays-charged particles accelerated to nearly the speed of light. If Earth were inside that danger zone, those cosmic rays would bombard our planet, stripping away ozone, heating the upper atmosphere, and increasing ground-level radiation for thousands of years. And we actually have evidence that this has happened not catastrophically, but measurably. In 2016, scientists discovered traces of a rare radioactive isotope called iron-60 in deep ocean sediments and even in soil from the moon. Iron-60 has a half-life of 2.6 million years and cannot be produced naturally on Earth. Its presence means that one or more nearby supernova exploded within about 100 light-years of us, roughly 2 to 3 million years ago. That timing coincides with strange climate changes and increased cosmic ray exposure inferred from other geological evidence. It may have even subtly influenced early human evolution by altering atmospheric ionization or cloud formation patterns. In other words, the death of a distant star may have helped shape the conditions for our own emergence. Despite all these dangers, the fact that complex life on Earth has persisted for billions of years tells us something crucial. We are protected by the vastness of space. The Milky Way sheer scala, 100,000 light-years across, makes direct exposure to these lethal events statistically very rare. Our solar system's position is also incredibly fortunate. We orbit within a relatively calm region of the galaxy, the so-called galactic habitable zone, far from the densely packed star clusters and supernova factories near the galactic core. On top of that, Earth's own magnetic field and atmosphere provide essential layers of shielding. Even when cosmic rays or gamma photons arrive from deep space, our upper atmosphere absorbs and scatters most of their energy. Our planet's magnetosphere deflects charged particles, greatly reducing our exposure at the surface. In a way, Earth exists in a cosmic sweet spot, not too close to danger, but not too far from the heavy elements that those same stellar explosions once created and scattered across the galaxy. But elsewhere in the universe, the story may be very different. In galaxies with higher rates of star formation, so-called starburst galaxies like Messier 82 supernova occur far more often, bathing entire regions in sterilizing radiation. Planets orbiting near these cosmic hotbeds of stellar birth and death would face frequent life-ending blasts. Even within our own Milky Way, dense star clusters such as the Carina Nebula or Westerland 2 are filled with massive, short-lived stars destined to explode. A planet forming in such an environment might never get the stability it needs to evolve complex life. In fact, this may help explain one of astronomy's deepest paradoxes, the Fermi paradox. If the universe is full of habitable worlds, where is everybody? Perhaps the answer is that many planets never get the chance to keep life alive for long. The same cosmic forces that make galaxies fertile with stars and planets may also keep them hostile to life. Today, a global network of observatories constantly monitors the sky for transient events, brief flashes of radiation that signal explosions billions of light years away. The space telescopes, like the Fermi Gamma Ray Space Telescope, the Swift Observatory, and the Integral mission, detect and triangulate new bursts nearly every day. Closer to home, astronomers keep a close watch on nearby candidates for future supernova, most famously Betelgeuse, the red supergiant in the constellation Orion, at about 640 light-years away. Betelgeuse is too distant to pose a direct threat, but it's close enough that when it finally explodes, it will be a spectacular sight, visible even in daylight. If a star were to go supernova within the 30-light-year danger zone, we'd likely know long before it happened. Early warning systems that track neutrino emissions and pre-collapse signals could give us years, maybe even decades, of notice to prepare observationally, though not to actually shield the planet. Fortunately, at present, no known stars massive enough to explode lie within that dangerous proximity. For now, Earth's skies are quiet. Even if one of these cosmic events were to strike, life is remarkably resilient. While a GRB or a nearby supernova could wipe out surface life, microorganisms thriving in the deep oceans or buried far underground would likely survive. Over time, life might re-emerge, adapted and fundamentally shaped by radiation and mass extinction. In that sense, cosmic catastrophes are not just threats, they are filters. They periodically reset the evolutionary clock, ensuring that survival favors adaptability and resilience. Perhaps without these violent cosmic purges, evolution would stagnate. The irony is profound. The same universe that creates the conditions for life also engineers the disasters that test it to its absolute limits. We orbit a small, stable star in a calm arm of a spiral galaxy, living in an epoch of relative cosmic peace. But we live amidst the remnants of ancient violence. Our atoms were forged in the hearts of stellar explosions, our planet was assembled from their scattered debris, and our biosphere evolved under a sky that is still capable of ending it all. Every element of our existence, the iron in our blood, the calcium in our bones, testifies to the fact that catastrophe and creation are not opposites. They are intertwined processes that together write the ongoing story of life in the cosmos. For most of human history, the night sky was a painting of perfect calm, a quiet, unchanging dome of stars. But that peace was an illusion. Behind the silence, the universe was exploding. It took us until the 20th century, with our new eyes and ears, radios, rockets, and space telescopes to finally see the cosmos for what it truly is, a realm of spectacular, universe-shaking violence. This is the story of how we learned to watch the universe explode. Our first clue wasn't a flash of light, but a strange, persistent whisper. In the 1930s, an engineer named Karl Jansky was trying to pinpoint the source of static messing with transatlantic radio calls. He built a massive rotating antenna and found something bizarre, a steady hiss coming not from Earth, but from the very center of the Milky Way. At the time, no one knew what it was. But that hiss was the first sign that space wasn't silent. Something, somewhere, was roaring. Decades later, during the height of the Cold War, the next clue arrived, and it was a big one. The United States launched top-secret satellites into orbit. Their mission? To watch for the gamma-ray flashes of clandestine nuclear tests. But the satellites started detecting flashes that weren't from Earth at all. They were coming from deep space, appearing at random, and then vanishing. These were the first ever sightings of gamma bursts, or GRBs. They were, without a doubt, the most powerful explosions humanity had ever witnessed. The only problem? We had no idea what was causing them. For years, GRBs were one of astronomy's greatest mysteries. These flashes of high-energy light are completely invisible to our eyes and pass through normal telescopes like ghosts. We could see the flash, but we couldn't tell where it was coming from. It was like hearing a thunderclap without ever seeing the lightning. Were these explosions happening in our own galactic backyard or across the universe? The mystery deepened. Then, in 1997, everything changed. An Italian-Dutch satellite named Beppo IZX caught a gamma-ray burst in the act. But this satellite had a trick up its sleeve. It could quickly pinpoint the burst's location and look for a fading afterglow in X-rays. This gave astronomers on the ground a target. For the first time, they aimed their optical telescopes at the afterglow and found it a tiny fading speck of light inside a faint, distant galaxy. A galaxy billions of light-years away. The implications were staggering. For a flash to be visible from that far away, it had to be mind-bogglingly powerful. We're talking about an explosion unleashing 1,000,000 trillion times the energy of our sun, all in a matter of seconds. It was as if an entire galaxy had blinked in agony, and we had just seen it. Humanity had finally witnessed the true scale of cosmic violence. From that moment on, the race was on to build a cosmic early warning system. In 2004, NASA launched the SWIFT Observatory. Think of it as the universe's smoke detector. SWIFT is designed to automatically detect a gamma-ray burst, swivel its telescopes to face it in under a minute, and send an immediate alert to astronomers all over the world. It was a game-changer. Suddenly, we weren't just stumbling upon these events, we were hunting them. 4 years later, the Fermi Gamma-Ray Space Telescope joined the hunt, giving us an even wider view of the high-energy sky. Together, SWIFT and Fermi transformed the study of GRBs. We went from a handful of mysterious flashes to a catalog of hundreds of bursts every year. And with all that data, patterns began to emerge. We learned there are two main types of these cosmic detonations. The long bursts, lasting more than 2 seconds, appeared to come from the collapse of massive spinning stars, a process that gives birth to a brand new black hole. The short bursts, lasting less than 2 seconds, were still a puzzle. The leading theory was that they were caused by something even more exotic, the collision of two ultra-dense stellar corpses, known as neutron stars. But we needed a new way of seeing the universe to prove it. And that new way came not through light, but through gravity itself. In 2015, the LIGO experiment made history by detecting gravitational waves ripples in the very fabric of space-time for the first time. It was like hearing the universe's hum. LIGO could hear the cosmic collisions of black holes and neutron stars, events that were previously invisible. Then on August 17, 2017, the breakthrough we had all been waiting for happened. LIGO detected the gravitational waves from two neutron stars spiraling into each other. Just 1.7 seconds later, the Fermi telescope detected a short gamma burst from the exact same patch of sky. It was the jackpot. For the first time in history, we had seen and heard the same cosmic event. We had confirmed that colliding neutron stars were the engines behind short GRBs. This was the birth of a new era in astronomy, multi-messenger astronomy, where we combine light, gravity, and particles to get the full story. The universe had just revealed its violence to us in stereo. Today, we're building even more powerful tools to map this violent universe. The Vera C. Rubin Observatory in Chile will soon begin scanning the entire night sky every few nights, creating a high-definition movie of the cosmos. It will catch thousands of transient events, from dying stars to mysterious flashes, giving us an unprecedented look at how the universe changes. And the James Webb Space Telescope is already on the case, analyzing the chemical debris left behind by these colossal explosions. It's helping us answer a fundamental question: where did the heavy elements come from? Because we now know that these cataclysmic mergers are cosmic forges. The collision of two neutron stars doesn't just create a black hole and a flash of light, it sprays the universe with newly created elements like gold, platinum, and uranium. Looking ahead, new missions like the Athena X-ray telescope and the space-based gravitational wave detector, LISA, will expand our senses even further. We are teaching ourselves to listen to the universe's stories, told in light, in gravity, and in the very fabric of space-time. And why do we do it? At the heart of these billion-dollar observatories and decades of research is that same simple human curiosity that made Carl Jansky point his antenna at the sky. What's out there? We've learned the cosmos is not a gentle place. Stars are born in chaos and die in fire. But these explosions aren't just acts of destruction. They are also acts of creation. Each supernova, each Gamma burst. Every stellar collision enriches the universe with the raw materials for the next generation of stars, planets, and maybe, just maybe, life. When we study cosmic catastrophes, we're not just watching distant violence, we are tracing our own cosmic origins. The iron in your blood, the calcium in your bones, the gold on your finger, all of it was forged in the heart of a dying star or in the spectacular collision of two long-dead ones. We are the quiet aftermath of ancient cosmic catastrophes. We are, quite literally, made of stardust. Every explosion we see across the cosmos is more than just a light show at S, a physics experiment written across space-time. And while we've mapped and modeled many of these events, the most profound questions are still ahead. Studying these cosmic catastrophes won't just reveal how the universe dies, but how it truly works. The explosions may be ancient, but their lessons are timeless. At their core, cosmic catastrophes are laboratories for the extreme. Nowhere else can we test the laws of nature at such staggering energies and densities. When a neutron star collapses into a black hole, or two of them collide, the forces involved are beyond anything a human experiment could ever reproduce. Matter gets compressed to densities of billions of tons per cubic centimeter. Magnetic fields twist so violently they can snap light itself into alignment. These are environments where quantum mechanics, general relativity, and nuclear physics all crash into each other, and where our current theories start to break down. The next generation of observatories like LISA, which will detect gravitational waves from space, and the proposed Einstein telescope, an underground detector, will help us watch these collisions in exquisite detail. By analyzing the ripples in spacetime, scientists could probe the inner structure of neutron stars, test if black holes truly obey Einstein's predictions, or even uncover signs of exotic physics like the elusive quark stars or boson stars that are theorized to exist just beyond the standard model. Every explosion is a chance to push physics to its breaking point and to see if nature itself breaks too. Every cosmic blast we see today is a message from the past. Light takes billions of years to travel across space, so when we watch a distant gamma ray burst, we're witnessing something that happened when the universe was young. Future telescopes, like the Extremely Large Telescope and successors to JWST, may soon capture the very first supernovae, the deaths of the universe's earliest stars, known as population 3 stars. These primordial titans, hundreds of times more massive than our sun, lived short, ferocious lives. Their deaths, likely as hypernovae, seeded the early cosmos with the first heavy elements. Seeing those first explosions is like watching the universe light its very first fire. On the other end of time, theorists also wonder about the final explosions, the last flashes of a dying universe, as black holes evaporate through what's known as Hawking radiation. They are predicted to release one final massive burst of energy before vanishing completely. These hypothetical black hole explosions, if they happen, will be the ultimate cosmic fireworks, a last violent sigh of space-time itself, billions upon billions of years from now. In the first and last explosions, the universe might just reveal its full story, from birth to oblivion. As strange as it sounds, the most destructive events in the universe are also the most useful to science. The gamma bursts and supernova we observe act as cosmic lighthouses, helping us measure vast distances and trace the expansion of the universe. Because certain types of supernovas shine with a predictable brightness, they serve as standard candles. It was by studying these very explosions that astronomers discovered one of the most shocking findings in modern cosmology, that the expansion of the universe is accelerating, driven by the mysterious force we call dark energy. Future missions, like the Nancy Grace Roman Space Telescope, will use exploding stars to measure dark energy with unmatched precision. Ironically, the deaths of stars may help us understand the universe's most subtle form of life, its accelerating breath. Even more exotic are the hopes pinned on gamma bursts themselves. Their incredible brightness makes them visible across almost the entire observable universe, potentially allowing scientists to probe regions and time periods too distant for any other method. In their violent death, stars illuminate the hidden geometry of the cosmos. Every explosion is also an act of creation. We now know that heavy elements, from the gold and silver in our jewelry to the uranium and platinum in our technology, are forged in the chaos of neutron star mergers and hypernovae. Without these cataclysmic events, there would be no rocky planets, no oceans, no DNA. In the coming decades, astronomers plan to use space-based spectrographs and multi-messenger observations to map out exactly where and how each element in the periodic table is born. By watching new kilonovae, the optical flashes that follow neutron star collisions, scientists can trace the cosmic origin story of matter itself, element by element. We may soon be able to point to a patch of sky and say, "That's where your gold came from." The universe's violent events don't wait for us to notice them. They happen anywhere, at any time. To keep up, astronomers are building automated sky networks that can detect and analyze these transient events in real time. Using artificial intelligence and global observatories like the Zwicky Transient Facility, astronomers can now identify a new explosion within minutes of it happening. In the near future, coordinated systems may allow us to witness a gamma burst, instantly trigger radio and gravitational wave detectors, and watch the entire chain of cosmic violence unfold across the spectrum, from XRAs to neutrinos. This is the dawn of real-time cosmology, a universe that alerts us to its own upheavals as they happen. Ultimately, studying cosmic catastrophes confronts us with a paradox that destruction and creation are not opposites, but partners. Every death in the cosmos gives rise to something new. Black holes, heavy elements, gravitational waves, even planets. Our own existence is the proof we are life, born from the ashes of ancient explosions. As we continue to explore the cosmos, the violence we witness reminds us that the universe's beauty is inseparable from its brutality. It is a universe that builds through chaos, evolves through fire, and renews itself through collapse. The more we understand these explosions, the more we realize that we and everything we love are products of a cosmos in constant transformation. Every second, somewhere in the universe, a star dies. Every few minutes, a gamma ray burst sweeps through the void, unseen by most. And every day humanity listens, catching the echoes of those distant detonations. Each explosion is a window into forces beyond our imagination, a reminder that we live in a universe that never stops changing. Violence and beauty, chaos and order, all woven together in a single cosmic story. From the ashes of dead stars, we have built telescopes, equations, and dreams, and turned destruction into understanding. This is not just a universe of catastrophe. It is a universe of creation, one that writes its story in fire and invites us to read it.